All right. Pardon me. So, good day. Hope nice weekends were had. Hope any and all festivities today are pleasant and much good food is involved. This week, we're going to be starting chapter 16, which is. Last chapter was about the formula, the law of. Wow, I'm tired, sorry. Coulomb's law, excuse me, the law that determines the electric force between two objects, that principle is sort of the reason that all electrical processes happen, is because of the force between electrically charged objects. And now we're going to start showing how that principle and the principle of the electric fields created by charged objects go on to specify everything else about electricity. In this particular week with chapter 16, we're going to be focusing on the electric fields themselves, certain applications of electric fields, and how they go on to inform things like voltage and capacitance, which are terms that you've probably heard if you've done much of anything with circuits or electrical engineering in the past. As a reminder, we will have excuse me, we will have lab this week because last week's lab was originally scheduled to be 2 weeks ago. So we will meet this Thursday for 2 electrical labs. I'll keep reminding everyone as we get closer to that particular date. Let me know if there's any questions or issues related to past or current material as of thus far. And if there's nothing pressing on your mind, then we can go ahead and get started. All right. So, Coulomb's law creates the electric force that then causes literally everything else having to do with electricity. All electricity is ultimately tied back to the electric force between charged particles. But from that one concept, scientists have taken it and applied it to a bunch of different situations. One of those being the idea of an electric field, which we started talking about last week, and we're going to continue that line of inquiry into this week. So, charged objects exert forces on one another. That's the entire point of Coulomb's law. That's the entire point of opposites attract and like charges repel. They do this via the medium of electric fields. Electric fields are the aspect of the charge that allow it to exert some sort of control over the universe a certain distance away from itself. And it's when the electric fields of two charged objects overlap that you start getting the Coulomb's law effects. Kind of like how, again, objects with mass exert gravitational fields, and when two objects' gravitational fields overlap, that's when you get gravitational force. So, you sitting on planet Earth's surface, your personal gravitational field is overlapping with Earth's gravitational field. Same thing with electrical fields. If something gives off an electric field, it's sending it outwards in all directions, and if it eventually overlaps with the field of a second electrically charged object, then those field lines will either kind of mix into each other and bend towards each other if they're opposite charges, or they will butt up against each other and clash and repel if they are like charged objects. And one, electric fields in general are very hard to see, so humans have had to come up with a lot of very odd ways to try to visualize them over the years. The pictures currently on screen are the same ones from last week. We've got a charged iron object surrounded on all sides by iron shavings floating in oil, and the iron shavings are lining up to the field lines. In addition to just single round objects, whoever took these pictures also used a variety of different shaped charged objects. And the purpose of this is to show that the shape of the object, assuming that the charge is uniform across the object's entire surface, the shape of the object can affect the shape of the field that it gives off. This upper left picture is just a point charge. And so it's radiating out evenly in all directions. But this second picture here, these two objects are still charged, but they're each slightly different shapes. One of them is basically an inverted teardrop, and the other is sort of just a bar. And their shape is consciously actively affecting the field they give off. And that's because, kind of similar to how pressure and force are related. If you exert pressure on a surface area, that force always has to push perpendicularly into that surface. All surfaces that are electrically charged and are creating electric fields create fields perpendicularly outward from that surface. So in the case of a circle, perpendicularly outward on every single square inch of that particular circle is always going to point outwards, radiating outwards like light shining off of the sun. But in the case of an object that isn't perfectly circular, if we look at the bar down here, it has flat edges to it. And for those flat surfaces, the field lines are all going to come out in the same direction, because from this entire flat line's perspective, perpendicular, for every single square inch of that flat part, perpendicular is always going to point straight up. Meanwhile, on the opposite face, on the other side of the object, perpendicular coming out of this face is going to point straight down. So for this particular object, the orientation of the field depends on which side you're looking at and what the shape of that side is. Notice that the ends of the bar are circular. It's rounded off at the edges, and at this round side here, it continues radiating outwards in multiple directions like how the sphere did. It's only the flat edges that send all the field lines out in a single direction. And you can kind of see that with the compounded teardrop shape as well. It has two edges that are mostly flat, and lines are coming out of those edges roughly perpendicularly to each other, in straight lines perpendicular to the surface, parallel to each other. Except for the rounded portion, where again it works like the sphere in the previous case, and also on the actual apex of the teardrop. In general, if a charged object has a point to it, the electrical effects on the point tend to get kind of weird, because if there's a bunch of charges jammed up in that point together, they're all fighting each other. They don't actually want to be anywhere near each other, and something's kind of forcing them near each other. So points on charged objects tend to kind of be the most electrically active. The field lines there tend to get the most chaotic. This is one reason why... Nope, that's a separate example entirely. I'll see if I can dig up a visual for the thing I'm thinking of later. So, different objects give off electric fields, and the shape of those fields depends more on the shape of the object than on the charge of the object. As a result, humans have been able to manipulate electric fields by changing the shape of the object making them. And we've been able to do that in some pretty interesting ways. For example, let's say that we take that bar, the straight, roughly rectangular shape, and we were to try to use that in some electrical applications. If we're just looking at the one flat surface, that one flat surface of this positively charged object is constantly going to radiate electric field perpendicularly out of its surface, and so all of these field lines just coming out of this one side are going to be parallel with one another. Mathematically, the effect that this has is, if we were to ask ourselves, what the strength of this electrical field is 1 centimeter away from this particular iron bar. We'll just keep calling it that. If we were to just like put an invisible check mark 1 centimeter away and ask ourselves, what is the strength of the electric field 1 centimeter away? It doesn't matter where on this invisible line 1 centimeter away is. Every point that is 1 centimeter away from the bar would have the same electric field, because every single point 1 centimeter away from the bar is getting these flat parallel lines. Whereas previously, if we were just looking at this point charge, this spot 1 centimeter away would have a different charge. Well, sorry, let me rewind. This spot 1 centimeter away from the point charge would have the same strength of field at this point 1 centimeter away, but the field would point in different directions. At this spot, the field points rightward. At this spot, the field points in this direction. Above it, 1 centimeter away, it points upwards. So the field is kind of less reliable because at every single point it's pointing in different directions. But with this shape, the field is all pointing in the same direction, which means every single point 1 centimeter away would have both the same strength of field and the field is pointing the same way. This is good for consistency, and humans like consistency if we're going to be using this to try to build some sort of a machine or a circuit. And as long as you know the charge of this particular object and the spot, like how far away you're examining, you could use one of the formulas we talked about last week, E field equals KQ over R squared, to determine the strength of the electric field that it is making. So if it's got a charge of 1 microcoulomb and we're looking 1 centimeter away, we plug in 1 microcoulomb for Q, 1 centimeter for R, and that would tell us a charge, an electric field at that position of 8.99 times 10 to the 7th Newton coulombs. So this shape is more consistent than the sphere is, because all the field lines are pointing in the same direction, and we like that for various applications. The same is true if you were to negatively charge this object instead, in which case, rather than sending field lines perpendicular out of itself, it brings field lines perpendicularly into itself. But all of these field lines are also still parallel, and if the charge of the object is the same, if it was still 1 microcoulomb, then the strength of the field would still be the same depending on how close you were to it. All that would change would be the sign on the answer, which just tells you the direction the field is pointing. Positive points out, negative points in. Now, the reason that I'm showing both the positive plate and the negative plate separately is because while these shapes are more consistent than the circular point charges, you still have the weakness of the field getting weaker the farther away from the plate you are. Doesn't matter what the charge of the plate is, doesn't matter what the shape of the plate is, if you get further away from it, the field gets progressively weaker. And in various specific electrical contexts that humans have been working on, we want the field to stay consistent. A lot of the time, if you're working with an electric field, you want to know exactly what the strength of the field is, and you don't really want it to be changing. You want it to stay consistent so that you can measure and calculate and count on its specific field effects. With these two separate approaches, having 1 positive bar and 1 negative bar, you can guarantee that the lines all point the same way, but you can't guarantee that the field will stay constant, because as long as you get nearer or further away from it, the strength is going to change. And so, some very smart people decided, Well, what if we put the two plates next to each other and had the field from one positive plate feeding into a negative plate? In this situation, say we just took the positive plate from before and the negative plate from before, and now we just physically have placed them such that there's kind of an electric field sandwich between the two. The two plates are the bread, and the E field between them is all the BLT goodness that you'd expect. If you were to measure the electric field within this configuration, you can pick any spot between the two plates, and the electric field will be the same. Because whatever spot you pick, say you pick dead center, you are equally close to the positive plate and to the negative plate. So you're equally under the effect of both. If you get closer to the positive plate, the effect of the positive plate gets stronger, but the effect of the negative plate would get as much weaker. The closer you draw to one, the further you draw away from the other, and vice versa. So with this configuration, with two plates both creating field and sending it inwards because they have different charges, well, I suppose two plates of opposite charge, the positive field feeding into the negative charged object, you've created a zone where the electric field is constant all the way inside of it. Doesn't matter where you are between these two plates, the field strength remains the same. Doesn't matter that you're getting further away from one plate because you're drawing closer to the other plate at the same speed. This object, this apparatus, is referred to as a capacitor. You've probably heard that term before in relation to electrical concepts. The physical design of a capacitor, an object referred to as a capacitor, is two charged plates, one positive, one negative, separated by some distance apart, creating a constant electric field between the two plates. It is a machine designed to create an area of constant, unchanging electric field, which again is very good if you need a nice, consistent field that isn't constantly changing based on where you are in the field. Normally, if it's just a single charged object making the field, its strength will vary based on how far away from it you are. And because fields are constantly pushing things away or nearer, things are constantly changing position within fields. This is the best way to create a constant, unchanging field that doesn't depend on your location. As long as you're between the plates, the E field is constant, which is good. And so that's what the term capacitor is referring to. So this is the physical device referred to as a capacitor. And that's what a capacitor physically is. What it does, I want to now talk about what it does, what its actual useful purpose is. When you build a capacitor, you've now created this area of constant, unchanging electric field. And what's useful about that is, if the field is constant and unchanging, it's going to exert a constant force, an unchanging constant force, on whatever charged object you put inside of it. Normally, if you put two charged point charges next to each other, and if they repelled, the further apart they get, the weaker the force between them will constantly be getting, and therefore they're not always going to be accelerating at the same rate. The force won't remain constant. But in this situation, if you were to, say, put a proton between these two plates, and you allowed the proton to naturally accelerate from the positive end towards the negative end, since the field doesn't change, the force, the electric force acting on that particular proton also doesn't change. It's going to be the same force is going to be applied to it the entire time. This means that if that force isn't changing, we can calculate it, we can continually rely on it to keep doing the same thing. That one constant force is going to keep doing the same amount of work on the charged particle as it moves from one side to the other. Therefore, since this particular field is able to exert a constant force on the charged particle as it moves from one side to the other, it's doing the same amount of work on that charge consistently every single time. What that practically means, for the sake of this class and what you can do with this particular machine, is, one, this thing can store charges inside of itself and store energy inside of itself. Because it's constantly, you know, if you put a charge in it, it'll take a certain amount of effort, a certain amount of time for that charge to reach the other side. One proton in here, we know it's naturally going to move away from the positive plate and towards the negative plate. Because the force is constant, you can count on, you can consistently know how long it's going to take the charge to cross from one side to the other. Which means you can store a certain amount of charges in here that will be released and discharged at a later point in time. You can put them in there and you'll know when they come back out. So capacitors can actually serve as batteries. They hold charge. If you put charge in it, it's going to hold on to that charge until later when it is eventually released again. So capacitors hold on to charges. You can charge them up, you can store charges inside of their electric field, and they will be released again later at a certain different point in time. But additionally, they can also store energy. And we know this because as a charge moves from one side to the other, the force from the electric field is acting on that charge as it moves some distance away. So this proton is going to move from the positive side towards the negative side, and it's going to move some distance away. The distance here being the distance between the two plates. That force is acting as the charge moves a distance, and force times distance is work. The capacitor, the field in the capacitor, is doing work on this particular charge. And conveniently, within the capacitor, the force doesn't change as it moves. So it's a constant force, constantly pushing the charge along, constantly doing work. That means that there's an exchange of energy going on here. When you put the proton within the electric field, it has a certain amount of electrical potential energy because of where it is in the field. Once it's allowed to start moving, that potential turns into kinetic as it's moving along away from the positive towards the negative. So this field can store energy and then release it by giving the energy to particles, and then they're allowed to move through the field and out the other side. So the primary function of a capacitor is to store charge and to store energy. So, vocab words again. The physical object known as a capacitor involves two electrically charged plates, one positive, one negative, separated some distance away, and there's a constant electric field between those two plates. The function of a capacitor is to store charge and to store electrical energy. So, that's vocab words. Excuse me. So, I've been hand waving a little bit. Let's actually look at the math that's currently on the right side of the screen. So we have this capacitor. There's an electric field inside of the capacitor, and it's going to act on this charge that we've placed within the electric field. that field is able to do work on the charge because it's exerting a force on the charge as the charge moves some distance. The distance here is going to be the physical width of the capacitor, so the change in location of this proton. So this is its starting point. It's going to end over here, and delta x would just be the distance between those 2 points. The force that the field exerts can be calculated by multiplying the charge, like the actual magnitude of charge of the charge, times the strength of the electric field. So Q times E. Strength of the charge times the strength of the field tells you the force the field is going to exert on that particular charge. This is, again, a variation of Coulomb's law. So field strength times charge strength tells you magnitude electric force, the force that field would exert on that charge. That force times the distance the charge then moves tells you the work that the field can do on that particular charge. The work that the charge... I keep getting my words backwards, I apologize. The work that the charge does... The work that the field does upon the charge, the work that the field does upon the charge is equal to what the charge's change in potential energy is going to be as it moves from one side to the other. I'm gonna redescribe gravitational potential energy real quick. This term showed up in Physics 1500. GPE, gravitational potential energy, is the energy an object has in a gravitational field based on its height, based on its ability to fall. And if an object in a gravitational field has GPE, that's because there's some distance within the field that it could be falling if it was allowed to do so. And once it begins falling, that GPE will turn into KE as it starts moving towards the ground, as it starts accelerating towards its final velocity. The exact same thing is happening inside of these plates. The exact same thing is happening in this E field. Just basically swapping out the word gravitational forces for electrical forces and gravitational fields for electric fields. When you put this proton in the field, it has a certain amount of potential based on where it currently is. Like, again, you raise a pencil above the ground, it has a certain amount of potential based on where it is, and based on where it will move within that field when allowed to do so. So at this point, the charge has a certain amount of electrical potential energy from the field, and when it's released and allowed to move, that electrical potential energy is going to decrease as it transforms into kinetic energy of the charged particle. So the particle begins moving, it begins accelerating, it now has a velocity, it now has kinetic energy. So, like with a falling object, the potential energy is turning into kinetic energy because of the work of the electrical field. And so that's this line here. The change in potential energy of the particle is equal to the work that the field is doing. The negative sign is there because if the field is doing positive work on the charge and, accelerating it up to some velocity, giving it kinetic energy, its potential energy is going to drop. So that's why that is there. All of this math combined can give us the formula here on the bottom. The change in the potential energy of our charged particle as it moves from one side to the other is equal to the work that the field is doing. And that work can be calculated by magnitude of charge times strength of E field times the distance the charge moves. And again, this charge moving through the electric field is virtually identical to an object falling down because of gravity. In both cases, you are moving within a field due to a force that field exerts on the object. That field and that force is doing work on the object to transform its potential energy into kinetic energy. And in the specific case of charged particles moving in electric fields, when those particles have kinetic energy, you have electricity. When charged particles are moving around because they have kinetic energy, that is electricity, because that is charges moving from one point to another. So electricity, the force that drives electricity is Coulomb's law, the electric force. The field that drives electricity is the electric field, and specifically, it's that field doing work on charged particles, exerting forces on them, changing their potential into kinetic, that allows electricity to happen. This is basically what happens inside batteries, too. Any battery, the charged particles inside the battery have some amount of potential energy that is turned into active moving kinetic electricity when the battery is plugged in and starts to be used. So the stored electrons, the stored charges within the battery have potential. Once they start being used, that potential becomes kinetic as the electrons begin flowing through the circuitry of whatever device you're powering. I'm doing a lot of hand waving. I need to take a minute to catch my breath from all the talking I'm doing. Any questions or its needs, etc. while I'm taking a quick break? I'm going to take a quick second. Any questions, needs, concerns, etc., let me know. I get paid to talk for a living. You think I'd get used to talking nonstop for an hour at a time by now. Okay. So, keeping in mind this bottommost part of the formula here, let's start applying it and using a little bit of math. My work is a little blurrier than I would have liked, sorry. So, let's say that we have a capacitor. We've built a capacitor. The plates of the two plates that we have used to build this particular capacitor are 0.01 millimeters apart. They're very close together. Most capacitors are very small. And the electric field between these two capacitors is 25 newtons per coulomb. The unit for electric field is newtons per coulomb, and that's because the electric field exerts force on charged objects. It exerts newtons on things with coulombs. So, two plates, 0.01 millimeters apart. The field between them is 25 newton coulombs. We're going to put a proton exactly between these two plates, and we want to know what its final kinetic energy is going to be as it goes towards the negative plate. Let me actually backtrack just a tick here. See if I can't change the picture to represent that. Whoops. There we go. So, we're going to drop our proton right smack in the middle between the two plates. We know from past experience that this particular proton is going to be repelled by the positive plate and attracted towards the negative plate. So we know it's going to move towards the right. No ambiguity there, no trick there. It's going to move towards the rightmost plate. It's not going to want to go anywhere near the positive plate. So, We want to figure out how much energy this particle is going to gain by moving through the field. So, it's the change in the particle's potential energy. The change in the particle's potential energy is going to be equal to negative Q times E times delta X. We need the charge of the particle, we need to know the strength of the electric field, and we need to know the distance the particle is going to move within that field. So, the charge of this particular particle, we are told that it is a proton. All protons have the same charge. There's a table in the chapter 15 notes. The charge of a single proton is 1.6 times 10 to the negative 19th. So that is going to be plugged in as our Q. Strength of the electric field is 25 Newton coulombs. And then there's a small little trick to this one, and that's figuring out what to plug in for delta X. Again, what the problem cares about here, since we're putting the proton in the middle of the field, so capacitor plates are out here, proton is here in the middle, the math cares about how far the proton ends up moving from where it begins. It's starting in the middle, and from the middle, it's going to move towards the negative. So it doesn't actually cover the entire distance between the two plates. It's going to cover half that distance since it's starting in the middle, and then from the middle moving to one side. So the delta X we plug in here isn't the entire 0.1 millimeters. It's going to be half of that. So what I've plugged into the math down here... Oh, shoot. I probably messed my math up a little bit now that I think about it. We need to convert the millimeters into meters. I think I actually messed that conversion up a little bit. I apologize. Whatever that conversion would end up being, you need to divide that number by 2 for this specific case, because it's starting in the middle, not because it's not starting on the far side and then moving towards the other side. So, something to keep in mind when looking at capacitor questions. You need to keep in mind where in the field the particle started. All that multiplied together can tell us the change in the potential energy of the particle as it moves from one side to the other. It gained this potential energy when you put it in the capacitor in the first place. It gained this potential energy by being placed in the field, and then it just had that energy based on where it was in the field. It's going to lose that potential energy as it starts moving, and it's going to turn into kinetic energy as it accelerates towards its top speed. So the change in potential energy, the decrease in potential energy from its starting point to its end point is going to be the amount of kinetic energy that it gains. So by finding the change in potential, we have also found the change in kinetic as well. Whatever potential it loses, it's going to gain as kinetic as it moves towards the other side. So that means we can plug our answer into the kinetic energy formula. Again, Ke equals 1/2 times mv squared. For this, we're going to need to know the mass of a proton, which is also always a constant. Mass of a proton is always 9. I'm all over the place this morning. That's the second I just noticed the second problem with my math. I am so sorry. I plugged in the mass of an electron, not the mass of a proton. So I made a mistake there. I apologize. We're told this is a proton. Mass of a proton is 1.67 times 10 to the negative 27th, I think. And I plugged in 9.1 times 10 to the negative 31st, which is the mass of an electron. So that's an issue with my math here. The method still works, but I plugged in the wrong constant. I apologize for that. Sorry. Method would still work, but you'd need to plug in the mass of a proton instead. So you could still use this to find the velocity, but the actual velocity would be a lot smaller than the one that I currently have listed here, because the mass of an electron... Oh, wait. Yeah, mass of a proton is bigger, so the resulting speed would be a lot smaller. So, my apologies. Sorry. I'm going to try to fix this work for the notes that are on Brightspace. Trying to make it a little clearer, too. I apologize. But this is what happens with this process here. The formulas being used here, the applications of those particular formulas. Change in potential energy from the force of the electric field on the particle as it moves tells you the change in its potential energy as it goes from its current position to its end point. That change in potential is going to be its gain of kinetic energy. And you can use that kinetic energy in the old-fashioned kinetic energy formula to calculate particle speed. And that doesn't matter. Like, this method will work regardless of what type of particle you put in any field. This would work too if it was an electron. The only difference is the electron would just move in the opposite direction. Additionally, we put our particle in the middle of the field. If you were to put a proton right up against the positive plate, it would have even more potential energy to start with, because it would be even closer to the thing it wants to get away from, and then it would have even further to move to get to the other side. So to kind of maximize the energy gained in this particular, it's basically an accelerator. Like, you're launching charges from one side to the other. To maximize the energy increase, you'd want to start on all the way to one side and then let it go all the way to the other. Let's apply this to one quick sample question. Again, same basic principles, but my math should be right this time. I apologize. So let's put a proton in a different capacitor. So different capacitor, different electric field. This new capacitor, for this next question, has a charge of 10 Newton coulombs. Sorry, an electric field of 10 Newton coulombs. Sorry. That proton is going to travel all the way from the positive side all the way to the negative side. And as it crosses, its final velocity is going to be at 343 meters per second. How far apart are the two plates of this particular capacitor? So, same formula, same basic method. Change in potential energy is going to equal the change in kinetic energy. The change in potential energy is going to be charge times E field times distance moved. And in this particular case, delta X is what we're going to be solving for, because we want to know the distance between the plates. We want to know how far the proton is going to move from one side to the other. And this question does tell us it's going to travel the complete distance between the two plates this time. It's not starting in the middle. It's starting on the positive side, and it's going to end on the negative side. So in this case, our delta X is going to be the entire distance between the plates, and that's what we want to find this time. That change in potential energy is going to be equal to the change in kinetic energy of the particle. We know the particle's final velocity, so we know, or we can figure out how much kinetic energy it would have on the end. And we will then plug in our numbers accordingly. So charge of the proton is still 1.6 times 10 to the negative 19th. Strength of the E field is now 10 Newton coulombs. Delta X is what we're solving for. Mass of the proton is 1.67 times 10 to the negative 27th. And final velocity is 343, which will then be squared. This will give us a final plate distance if we solve for delta x of 6.14 times 10 to the negative fifth meters. Very small capacitor. These plates are not very far apart. I didn't make any mistakes in this math. I apologize very much about that last example. Not sure what happened there. Here is the same methods and the same formulas applied without those errors in it. And I want to briefly show you what an actual capacitor looks like on the inside. Again, all the plate distances that we've looked at for examples so far are all very small. They're all very close together. This picture currently is the inside of a capacitor. And like if you were to go to, say, Radio Shack, assuming those are still open, and buy a capacitor for use in a circuit, the actual object that you would be given would be something kind of the size and shape of a soda. Well, it'd be the shape of a soda can, but it would be, about the size of your pencil eraser. And it would have two metal wires coming out of it that are, the two ends of it as a... It would have two metal wires that are like the two different sides of the electrical component. Electricity goes in one side and comes out the other. Within that little tiny shape, about, again, the size of a pencil eraser, is a structure similar to what is currently on screen. It's a bunch of plates stacked across each other. Each of these plates has an electric charge, and there's constant field between all the plates. In an attempt to sort of maximize what one small capacitor is able to do, they tend to contain multiple plates all doing the same thing that we've been looking at all day today, so that you can get as much out of the one capacitor as possible. Multiple plates together has the effect of driving the capacitance up. So that's what the physical component looks like. And as we continue on in the course and in labs, we'll actually start building some circuits, and I actually will be able to show you what the physical capacitor object looks like and what it does in a circuit. Let me know if there is any questions, issues, needs, etc. at this particular time. Excuse me. We've been going on for a while, and it's been a very vocab word heavy day today. So I plan on us breaking here very shortly. Before we do have our break for today, there's one more quick vocab word that I want to just point out so that it can sit in your brain, and then we can explain it more as the week goes on. Within our capacitors that we've been talking about today, or really within any electric field, particles within that field are going to move from where they have high potential to where they have low potential. That's been the point of the math we're doing, is the charges move from the side of the field where they have high potential, where they have a lot of pent-up energy built up, to where they have less energy pent up and built up. So they're moving from high energy to low energy. Their potential drops as they move from one side to the other and gain more kinetic energy along the way. So as something moves through the field, its potential changes. There's a difference in potential from one side to the other. And this is the same thing with GPE and falling. This pencil has high potential up here and low potential down here after it's fallen. And all objects inherently move from high potential to low potential. That happens no matter what the field is. There's a synonym for that difference in potential from one side of the field to the other. And that word is voltage. The electrical concept of voltage represents the difference in potential between two different locations. We'll talk more about what that means and how we will use it next time, but I wanted to go ahead and get that vocab word in your head. The difference in electrical potential between 2 points in space can also be described as the voltage between 2 different points in space. And I'm hoping that voltage or volts is something you've encountered before, you've at least heard the word before. We'll talk more about what it means and how we use it next time. Let me know how all this information feels. Let me know if you have any questions, issues, needs, etc. If not, then we will have our break for today. I'll be hanging out here for the next hour if you want to hop back in with questions later. And if there's no questions right now, and if I don't see you again today, then I will see you tomorrow.